Howdy everyone, we're going to continue our talk about Chapter 5 now, continuing with enthalpy, which should be a familiar term to you from Chem 2. Enthalpy is when we account for the heat flow of a system, but at a constant pressure. This is coming from some advanced physical chemistry and physics equations. You do some derivation, all that. But if you just do some equation work, whatever, you end up with this, that enthalpy is the internal energy plus the product, so multiply, of pressure times volume at constant pressure. That's the rule. At constant pressure, we can use this. But then you might say, well, wait a second. We just spent all the last video saying we can't get E by itself. We can't get the total internal energy. We don't know it. And you're right. So we can't, while this equation is true, we can't use it directly. What we can do is, what about the change in enthalpy related to the change in energy? We could get the change in energy. So we say that, okay, well then the change in enthalpy is the change in this whole thing. And then if we do a little bit of math trickery with distributing, well then the change in enthalpy, the delta H, is going to be equal to the change in internal energy, delta E, plus the pressure times the change in volume, because again, pressure is constant. So that's why that doesn't have the delta in front of it. Otherwise, this would be a bit too complicated. But now we can say, oh no, the pressure stays the same, so we just need our change in energy and our change in volume. All right? Well, now we're going to do another math substitution. We said earlier that the change in energy was the heat plus the work, Q plus W. And we also know that work is negative P times delta V. We just got that at the end of our last lesson. If we plug both of those in, well then wait a minute, this delta E becomes Q plus W. This plus P times delta V becomes negative W, because that negative sign there. Well, that just means that delta H is equal to Q. Our enthalpy at constant pressure is equal to the heat flow, and that's great. Now, a lot of times Q will just be measured directly in joules, and a lot of times when we do some other experiments, the delta H will be in joules or kilojoules per mole. So they may not always be the exact same number, but they're coming from the same place. One is just standardized to per mole, or one of them is specific to a certain reaction or a process. All right, but at constant pressure, the change in enthalpy, the delta H, is equal to the heat gained or lost. All right, well, let's talk about what does that mean. Well, we said a positive Q was endothermic. Well, that means a positive delta H is also endothermic. A negative Q was exothermic, energy was released. A negative delta H is also exothermic. So same, here's our picture again, heat going in or heat going out, how that affects the delta H. All right. Enthalpy of reactions. You'll see it written here a lot of times, this delta H RXN, saying if we do a reaction, what's the delta H of it? It's always products minus the reactants. What's the enthalpy of all the products minus the enthalpy of all the reactants? We did this in Chem 2. We had to, we looked them up on tables or they were given in the problem, but you'd say, okay, here's all my products, put them together. Here's all my reactants, put them together, watch for balancing. And then it was, okay, products minus reactants. And you see it's going to be equal but opposite if you do the opposite reaction. So negative 890 dropping down or positive 890 going up, depending on which way the reaction's going. But that quantity, again, it's the enthalpy of reaction or the heat of reaction. A lot of times we'll say heat. And so here they just give an example. We have hydrogen and oxygen mixed. A spark is applied. We get our lovely explosion to form water. And heat is released. So, okay, we start it here with the enthalpy of the hydrogen and oxygen. It drops down to form the gas water. And so that means our delta H is negative. This was exothermic. All checks out. All right, so a few reminders here that they want to give us. Enthalpy is extensive. It does depend on the amount. So this is why a lot of times the delta H is standardized to delta H per mole to say, oh no, well, here's how we can calibrate it. But officially, it is extensive. If you have more of a reaction, you'll have a larger delta H. Less of the chemicals, you'll have a smaller delta H. But it will be the same delta H per mole. The change is equal in magnitude but opposite if it's the reverse process. So that was the negative 890 and the plus 890. And the change of reaction does depend on the states because there's intermolecular forces between the different molecules. There is a different change in heat if you're going to water vapor versus liquid water. It's about a 44 kilojoule difference in heat per mole. So the state of matter is important. So if we look up values in the book here to do some of these problems later on, if it says gas, you got to make sure you find that chemical as a gas. If it says liquid, you got to find that chemical as a liquid, and so on. The state does affect the numbers, it affects the outcome. All right, so how do we get these delta H's? Right? We said, okay, well, we can't get E, we can only get delta E. We can't get H, we can only get delta H. How do we get delta H? How do we get that Q that we need? And for that, we use calorimetry, coming from calor, right? Latin for heat, and then metry, measuring. So measuring heat is what we call this, calorimetry. And so the device we use is a calorimeter, and they have a nice diagram here of a really, really cheap one, and yet also fancy with this cork stopper and the stirring rod. But this is often called a coffee cup calorimetry setup, where you have two styrofoam cups. One styrofoam cup does a decent job of holding heat in or keeping heat out. But you know, if you have held a styrofoam cup of hot chocolate or coffee or tea, you still feel warmth. So we often use two styrofoam cups to have like a double insulating layer. This air gap in between helps keep the heat where it started, or you know, where it needs to be. We have a stirrer, if you can. That's why this one's fancy. It has this cork top where you can spin the glass stirrer to spin the blades. A lot of times we sometimes just don't have that, so you gotta maybe have just a regular styrofoam cup lid where you use a straw or a thermometer to stir it up, or you just shake it. You do the best you can. Ideally, there's an actual stirrer, and we have a thermometer, so we can measure the temperature before the reaction and measure the temperature after the reaction. And sometimes even we measure it at different times to get better data. Sometimes there's some fixes we want depending on how our setup is. Well, how are we going to use that to get our calculations? Well, we have two terms here, heat capacity and specific heat. They are related, but they are not the same thing, so we want to make sure we can tell them apart. The heat capacity, as it says here, is the amount of energy needed to raise the temperature of a substance, and I'd like to say a sample of a substance, by 1 degree Celsius or 1 Kelvin. But that depends on the amount. That heat capacity is an extensive property. And so a swimming pool has a larger heat capacity than a cup of water. Because there's a lot more water in the pool, it takes a lot more energy to warm it up, right? If you have a pool, or if you go to a community pool in the spring, it's like, oh, it's really cold at the beginning, because it takes a lot of energy to heat that pool up, so it takes time. Cup of water, throw it in the microwave for a minute, you're good. It doesn't take nearly as much energy. All right? Then the other term here is the specific heat. This is, what about 1 gram for that substance? So it doesn't matter if it's 1 gram in a swimming pool or 1 gram in a cup. How much does it take to make 1 gram of that material increase by 1 degree? And that's where we say it's the specific heat. And then the third term here is the molar heat capacity, which is just the same thing but per mole. How much heat per mole? Specific heat, though, even though it's per gram, is the more commonly used one because in calorimetry, we're measuring grams, right? We're going to measure how much water did we put in, or how much of this other chemical did we put in, and we're measuring that in grams. So specific heat tends to work out. This is something that you might remember from biology class. One of the important properties of water is that it has a very large specific heat. So if you see here, compared to these others, whether it's a gas or even a solid or a liquid, all these others, right? Methane's at 2.2, that's not so bad. But a lot of these are at around 1 or even much less than 1. And water's at 4.18. So water's got a large specific heat. It takes a lot of energy to make water go up in temperature. And that's also why it takes a long time for the water to come back down in temperature. All right? And so here's our schematic here on the right. If we have exactly 1 gram of water at 14.5 degrees Celsius, it will take that 4.184, that's more sig figs, same number there, 4.184 joules, or 1 calorie of heat, to make it increase to 15.5 degrees Celsius. So that's what we mean by that. All right? Well then, how can we put that together? How can we use that? Well, for constant pressure calorimetry, that's our coffee cup calorimetry again, where air can leak out. We're trying to keep things from flying out or spilling, but stuff can get through there. So that means the air pressure will make sure we always have the same pressure over the course of that experiment. So we can say, well, if the reaction is releasing heat or taking heat in, it's going to take in or release that heat from the surroundings, which is all this water here, all the stuff it's dissolved in. And so we can't measure the chemicals directly, but we can measure the water. And so we usually use the 4.184. If the problem gives you another number to use that. But for dilute solutions where it's not too concentrated, we can still use about 4.184 or thereabouts. And we use this equation that the delta H, because it's the same as Q, is the calorimetry constant, or sorry, not the calorimetry constant, that's the next one. The specific heat, which you would look up, so okay, that's the 4.184 for water, times the mass of the solution, so that's going to be how much water did we use, how many grams of the other chemicals did we use, just throw that all in there, and then times the change in temperature. And once again, this delta is final minus initial. So you'd say, what's my final temp minus my initial? If you multiply them all together, you'll get the heat of the solution, because we're measuring the temperature of the solution. But what we want is for the reaction. The system is the reaction. So that's why over here we see, oh, it's the Q of solution, or it's the negative Q of the reaction. Because again, conservation of energy, it must be an equal amount of energy, just opposite sign. And so this is how we'll get this. Now on the AP test, they're a little tricky. They give you this equation, but they don't mark it as solution. They just say Q. So it's up to you to remember on the AP test, if this comes up in the free response or somewhere else, that you need to say, okay, wait, when I multiply my specific heat times my mass times my delta T, that gives me Q of solution. I have to flip the sign on my own so that this makes sense. So this is where we want to say, hey, if my final Q is negative, that means exothermic. Does this look like exothermic? Did that temperature of the surroundings go up? Did it release energy? So you got to kind of do these mental double checks, because the AP test does not give you the entire equation. They just say Q and make sure you know what you're doing. But basically it's plug in the specific heat, constant given, plug in the mass, be given in the problem, plug in your delta T, you get it from the problem, just plug them all in, get your Q, and flip the sign. That's how you get Q for your reaction. If it's a coffee cup calorimetry. The other type of calorimetry is a bomb calorimeter. And so a bomb in this case is something designed explicitly not to explode. We don't want it to blow up. It's the opposite of that. So what happens is it's completely sealed. We have this chamber inside that's all sealed up. There's an electric lead that goes in there, because you're going to have a little wire that acts as like a spark plug to make a reaction start. This is for combustion reactions. That chamber is then completely surrounded by water in its own insulated chamber. And so we're going to measure that water. So it's going to be stirred up really nicely with our stirrer. We'll have a nice thermometer in there. Excuse me. When I did this an experiment of this in college, I remember it was a really nice thermometer that had 2 decimal places, not just one, so we could get better data and really see the temperature change. But in this case, you don't have to worry about the mass, because you're going to use something called the calorimeter constant for this one. And that's where it takes in how much water did you put in there, and the mass of it, and this holds sealed thing together. And so if you're running multiple experiments at the same time in the same calorimeter, then it's the same number. So a lot of times what you'll do, you'll open this up, you'll put a known sample in that's a standard, usually it's benzoic acid. You probably don't need to know that. But when you put that in there, you measure how much you use and all that stuff, you run the experiment, and you calculate this, because the Q for that reaction is very well known. Then you'll take that sample out, put your next sample in, hook it all up, do it again. And now you can use the calorimeter constant you got from the first experiment, plug in your delta T, and now calculate your Q for the other one. Notice here that this is also equal to a Q of the surroundings, and then the negative would go. They just decided to not put that part, put the negative here, but it's the same thing. We measure the heat flow here, and then flip the sign to get our Q for the reaction. Now it's not the exact same, because enthalpy should be constant pressure, and if you're burning something up in a sealed chamber and gas is produced, pressure is going to change. So there is a slight error there, but as they say here, it's a pretty good approximation. It's not going to be exact, but it's pretty good. All right, here we go. I forgot that I had this slide. So because the volume's constant, this actually gets delta E, not delta H, but it's probably going to be a very small change between the two. I'm going to stop there for this one. We had a lot of talk about enthalpy and how we calculate it for calorimetry. In the next video, we'll talk about other enthalpies and how we can put this all together. All right, see you later.